Industrial nanotech's industrial promise is moving from hype to hard choices. Industrial nanotech is getting a fresh spotlight this week, not because of a single blockbuster breakthrough, but because the people who regulate, fund, and scale technology are sharpening the same message. At once, the science is maturing, and now the hard part begins. What's changing right now is the focus. The conversation is shifting from, can this work? To can this be manufactured, tested, insured, and trusted at global scale? That shift matters because nanotech already sits inside everyday industrial systems, from thin film coatings to battery materials, and the next wave targets bigger markets with higher stakes. This piece explains what says industrial nanotech in real-world terms, why safety standards and measurement are suddenly central to commercialization, and how geopolitics and supply chains are shaping who gets to lead. The story turns on whether industrial nanotech can scale without losing control of quality, safety, and trust. Key points. A new push around safety testing and measurement for manufactured nanomaterials is bringing standardization to the center of commercialization, not as bureaucracy, but as an enabler of scale. Europe is explicitly framing advanced materials as a competitiveness and decarbonization lever, while warning that leadership in disruptive areas like nanotechnologies is contested. Industrial nanotech is increasingly sold as infrastructure, coatings, catalysts, and materials, platforms that slot into existing factories, rather than headline-grabbing consumer gadgets. The biggest bottleneck is no longer novelty in the lab. It is repeatability in production, consistent particle size, purity, surface chemistry, and performance across millions of units. Safety and environmental questions are becoming more operational and less theoretical, with emphasis on reproducible test methods and realistic exposure measurement. 3 broad scenarios are emerging: fast scale-up with strong standards, slower adoption through fragmented rules, or a 2-speed world split by geopolitics and supply chains. Background: nanotechnology is a toolbox, not a single product. It refers to engineering materials and structures at the nanoscale, where size and surface effects can change how something conducts electricity, blocks oxygen, absorbs light, or catalyzes a reaction. Industrial nanotech often shows up in 3 forms. First, nanoparticles mixed into other materials to strengthen, lighten, or change chemical behavior. Second, nanostructured surfaces and coatings, including ultra-thin films that control corrosion, friction, or permeability. Third, nanoscale device features, which are foundational in modern electronics and increasingly important in sensors and photonics. For years, the promise has been clear: better batteries, cleaner chemical processes, tougher construction materials, smarter packaging, and more efficient industrial equipment. The frustration has also been clear: scaling is difficult. When a material's performance depends on tiny details, manufacturing becomes a discipline of measurement, process control, and quality assurance. That is why safety testing and standards have become a front-page topic in the nanotech world. If a material cannot be tested consistently, it cannot be regulated consistently. If it cannot be regulated consistently, it becomes hard to ensure, hard to procure, and hard to deploy at scale. Analysis. Political and geopolitical dimensions. Industrial nanotech is now a competitiveness story as much as a science story. Advanced materials sit inside energy, defense supply chains, semiconductors, and critical infrastructure. That makes nanotech policy adjacent, even when the work is happening in private factories. This week's framing in Europe is a good example. Advanced materials are being treated as a strategic category tied to decarbonization, industrial capacity, and reducing dependencies. The subtext is blunt. If the next generation of materials platforms is dominated elsewhere, downstream industries become more vulnerable to price shocks, export controls, and supply disruptions. At the same time, nanotech is an awkward policy object. It is everywhere, but rarely labeled. A battery maker might be buying advanced conductive additives, not nanotechnology. A packaging supplier might be adopting a new barrier coating process without marketing it as nanotech at all. That invisibility slows public debate, but it also means policy can lag deployment. A geopolitical split is plausible. In one world, standards and test methods converge enough to let suppliers sell globally. In another, companies end up qualifying different material formulations for different blocks, raising costs and reducing speed. Economic and market impact. The industrial promise of nanotech is not mainly in selling expensive nano products. It is in selling performance upgrades that pay for themselves, longer shelf life, fewer defects, lower energy use, lighter structures, and smaller failure rates. That creates a specific kind of market dynamic. Buyers want proof under real conditions, not lab demonstrations. They want stability across time, temperature, humidity, and imperfect handling. They also want supply reliability. If a nanomaterial requires rare inputs, fragile processing, or highly specialized equipment, procurement teams will treat it as risk. A vivid recent example is the push to commercialize ultra-thin barrier coatings for paper packaging. The business logic is simple. If paper can match the barrier performance of metallized plastics, for certain uses, companies get a sustainability win without sacrificing shelf life. The industrial challenge is harder. Do it roll to roll, at speed, with uniform coatings over huge areas, and with quality control that catches failures before they hit the market. This is what nanotech going industrial looks like. Less sci-fi, more process engineering, technological and security implications. The core technical shift is the move from discovery to discipline. At industrial scale, it is not enough for a nanoparticle to be about the right size. It has to be within a tight distribution. Its surface chemistry has to stay stable across batches. It has to behave the same way after shipping, storage, and integration into a larger product. That is why safety testing guidance and measurement topics like dosimetry are getting renewed attention. Put simply, if you cannot measure what dose a test system is really experiencing, you cannot compare results across labs or across products. If you cannot compare results, you cannot build reliable rules. An industry cannot confidently scale. Security implications arrive through dependency. When nanotech becomes a materials platform for electronics, energy storage, or critical coatings, the supply chain becomes strategically sensitive. Control over precursors, equipment, and know-how can translate into leverage. Social and cultural fallout. Nanotech still carries a trust problem because the word nano triggers two competing instincts: awe and unease. The public concern is not irrational. Tiny particles can behave differently in bodies and ecosystems than larger particles. The industrial problem is that fear does not need to be scientifically precise to be economically costly. A single high-profile contamination scare or unclear health claim can slow adoption across entire categories. That is why clear testing practices matter beyond compliance. They are a social license tool. They let companies and regulators separate legitimate risk from vague anxiety, and they reduce the space for misinformation to fill the gap. What most coverage misses. Most coverage treats regulation as a brake. In industrial nanotech, regulation quality measurement is often an accelerator. When a sector agrees on how to prepare samples, characterize materials, and run tests, companies can spend less time arguing over methodology and more time improving products. Investors can underwrite scale up with more confidence. Buyers can write procurement standards that make sense, instead of bespoke checklists that lock out smaller suppliers. There is a second overlooked factor. Industrial nanotech success increasingly depends on boring infrastructure like reference materials, data standards, and shared methods. These are not glamorous breakthroughs, but they are what turn a field into a market. Why this matters for industrial nanotech. In the short term, the biggest impact will be felt by industries already leaning on advanced materials. Packaging, batteries, coatings, construction materials, electronics, and industrial chemicals. The immediate question is not whether nanotech will be used. It already is. The question is which approaches become the default, and which remain stuck in pilot projects. In the long term, the stakes are larger. If industrial nanotech platforms mature, they can raise the efficiency ceiling of entire sectors. That matters for inflation-sensitive supply chains, for energy transition timelines, and for national competitiveness. Concrete events to watch next are less about a single nanotech moment, and more about the rollout of standards, guidance adoption, by regulators, and whether large manufacturers commit to multi-year procurement contracts that pull suppliers into mass production. Real-world impact. A factory manager in northern Mexico is under pressure to reduce packaging waste without increasing spoilage. A new paper-based barrier option looks promising, but the manager needs proof that it will run on existing lines without raising defect rates. The decision hinges on repeatability, not headlines. A construction materials buyer in the Middle East is offered a nano-enhanced additive that claims higher strength with less cement. The buyer likes the decarbonization angle, but asks for long-term durability data and a clear handling protocol for workers. The project moves forward only if the supplier can provide consistent batch certification. A battery supply chain analyst in South Korea sees a new nanomaterial additive that could improve charging performance. The analyst's first question is not performance. It is whether the precursor supply is stable and whether export restrictions could turn a materials upgrade into a production bottleneck. A health and safety lead at a research-intensive manufacturer in Germany updates workplace controls for powders and aerosols. The goal is practical: protect staff, reduce uncertainty, and avoid future liability as nanomaterials become more common in products and processes. Road ahead. Industrial nanotech is entering a phase where the limiting factor is no longer imagination. It is governance, measurement, and manufacturing discipline. The fork in the road is clear. One path builds shared methods and predictable rules that let companies scale safely and compete globally. The other path fragments into uneven standards, slower adoption, and higher costs, with geopolitics shaping who can sell what, where. The early signs will show up in mundane places: which test methods become default, which standards get embedded into procurement, and which pilot plants turn into real facilities with repeat orders. When those signals align, the promise becomes a supply chain